In this segment on central force motion, we're going to introduce the concept of a central force. We're going to talk about why is it that we need to focus our energies on understanding the general mechanical problem of motion of a particle under central force. Let's look at what is a general mechanical problem. Which we might seek to solve as a consequence of Newton's second law. Newton's second law essentially says that any mechanical problem can be understood as a computation of its trajectory r of t, right? Or in other words, x as a function of t, y as a function of t, and z as a function of t. We can compute this trajectory, which is the most detailed information that we can have about the system, by using the Newton's second law, which is mass times the acceleration is equal to the force acting on the particle. This is the force of influence which results in the motion that the particle displays. Now the force F in general can be dependent on the location of the particle. It can depend upon the velocity of the particle. It could also be that the force itself changes explicitly in time. Let's look at some of these examples. I'll give you an example of a purely position dependent force. This is Sun, this is Earth, this is the position of Earth with respect to Sun. The force which is exerted on Earth by Sun can be written as gm, the mass of the Sun, times the mass of the Earth divided by r square times minus r cap. Why is this a position dependent force? Because the force F, which acts on the Earth when it is at the location xyz, can be given the form minus g mm small n upon r square, which is x square plus y square plus z square, times r cap, which has the form xi cap plus yj cap plus zk cap divided by x square plus y square plus z square to the power half. Or in other words, this force law takes the form minus gmm xi cap plus yj cap plus zk cap divided by x square plus y square plus z square to the power 3 over 2. So it's clear that as the Earth changes its position, the force on it changes. This is the sense in which we refer to the force that acts upon Earth as a force field exerted by the Sun on the Earth. But very simply, it's a position dependent force which is acting on Earth. Let me go over to example 2. Here I give you an example of a velocity dependent force. Think of a region where there is a magnetic field present. Call this magnetic field B. B itself could be a function of x, y, and z. There is a source which produces this magnetic field B. Assume the source is likely to be consisting of currents. We will assume that these currents are static, and as a result of that, The magnetic field that it produces does not change with time but could change from point to point in space. In such a field, there is a charged particle of charge q moving with velocity v of t, where v of t is nothing but r dot of t. If such a particle were moving in a magnetic field B, the force acting on it is going to be given by q r vector dot crossed with b x y z. You can write this as q x dot I cap plus y dot j cap plus z dot k cap crossed with p, which is a function of x, y and z. This is in fact an example of a force which is both velocity and position dependent. Should the magnetic field B be completely uniform in that it doesn't change from point to point in space, this would be a purely velocity dependent force. Let me give you a third example of a purely time dependent force. Both the previous examples, the time only entered into the force by way of its dependency on position and velocity, but forces could also be explicitly time dependent. Consider the region between parallel plates of a capacitor and assume that this capacitor is hooked up to an AC source. As a result, the electric field in the region between the capacitor plates continuously bobs up and down in a manner given by E is equal to E0 cos omega t, assuming a general direction of n perpendicular to the plates of the capacitor. If a charged particle is present in the region between the plates of the capacitor, a force F gets exerted on it given by Q times E naught cos omega t n cap. You can clearly see that this force is exclusively dependent only on time t and has no dependency on position and velocity. With that backdrop of forces which are dependent on position, velocity and time, I'll introduce a special class of forces called as the central forces. A central force F is a particular kind of a position dependent force in that its magnitude F is dependent only on the radial distance from the origin to the particle and its direction is purely radial. Let me showcase this through a small diagram. This is X, Y and Z. The particle is present here at time t. R is the distance between the origin and the location of the particle. Then the force only depends upon the radial distance. On the other hand, the direction is exclusively along the radial direction. If F has a negative sign, then the force could also be pointing along the minus r cap direction. Examples of these would be the gravitational force on Earth. We had seen that F is given by minus g m small m upon r square r cap. Here F of r is given by minus g m small m divided by r square, and it's explicitly negative for all values of r. A second example is that of a charge capital Q which is held static at the origin of a coordinate system. At some distance r, there is a charge small q. The force exerted by small q force exerted by capital Q on small q, provided q were at rest, or for that matter even if it was moving, would be 1 upon 4 pi epsilon naught q small q divided by r square r cap, exactly like the way it would be with the gravitational force, in that f of r would be given by capital Q small q divided by 4 pi epsilon naught r square. But here is an interesting difference. If the product of q into q is greater than 0, which can happen if both q are like charges, then f of r would be greater than 0 and in fact would be pointing along the positive radial direction. On the other hand, if they are unlike charges, then capital Q times small q will be less than 0 and f of r would be explicitly negative, pointing along the minus r cap direction. So there you have it. Central force motion problem consists of the study of the motion of a particle of mass m under the influence of a force F given by f of r times r cap.